In this lesson, we will cover the CPU memory areas and addressing in a SIMATIC controller. The load memory is implemented as either a memory card or integrated into the controller based on the model of the CPU. Your user program and hardware configuration will be stored on the load memory. You can think of the load memory as like being the hard disk on your personal computer. The work memory is implemented as RAM memory. This is for the executing program. Think of this as like being the RAM memory on your personal computer. There is also retentive memory that is implemented as non-volatile RAM. You can configure what memory areas will be stored in the retentive memory area so that on a power cycle you can bring back the values before the power cycle. The system memory area is also implemented as RAM. Your process image input table and process image output table is stored in the system RAM. Inputs would be designated by I, outputs would be designated by Q addresses. Your bit memory would be M addresses. Your SIMATIC timers and counters would be T and C addresses. Your local data or temporary local data would be L addresses. There are also registers stored in the system memory. System messages in the form of the diagnostic buffer. On your programming device, you will store your Step 7 project. Your Step 7 project will contain your logic blocks, data blocks, your comments, and symbolic information. When you transfer your Step 7 project from your programming device into the load memory of the controller, the logic blocks and data blocks will be transferred into the load memory. The symbols and comments will not be transferred into the controller. Those are only going to be available on your programming device. Once your program is loaded into the load memory of the controller, the execution relevant portions will be transferred into the work memory. The controller uses byte-based addressing, so the smallest unit that you can address is a single Boolean bit. The individual bits are going to be stored within bytes in the controller. So M0.0 would refer to the first bit in the first byte of the controller. A byte address, like MB0, would consist of 8 individual bits, bit 0 through bit 7 within the individual byte address. A word address is 16 bits, so MW0, the 0 is your starting byte address, so for a word address it would use byte 0 and byte 1. For a double word address, such as MD0, the starting byte address would be 0, so it will use the starting byte address plus 1, plus 2, and plus 3. So MB0, MB1, MB2, and MB3 would all make up your 32-bit double word address. So when we look at MB0, it's going to consist of 8 individual bits, bit 0 through bit 7. If we look at the address MW0, 0 is the starting byte. So that means that the first byte in this word address would be MB0, and then the second byte in that word address would be MB1. So whatever your starting byte address plus 1 would be the 2 bytes used for a word address. So MW0 would consist of MB0, MB1. For double words, MD0 would consist of 4 bytes or 2 words. So MB0, MB1, MB2, and MB3 would be the 4 bytes that make up your double word. And you could also say that it would be 2 word locations. MW0 and MW2 would make up your 32-bit word. In the controller, here's a picture of how the memory is laid out. So we have your process image input area, so the values from your input cards would be transferred into the process image input area that resides in the system memory of the controller. When your logic updates, it will update the process image output area, and then the process image output area will be transferred to the output cards. The M memory area, or the bit memory, is internal to the controller. You can have multiple data blocks in the system, like DB1, DB2. In this example, I'm using DB10. If I want to address an individual bit, I can use the syntax I byte number dot bit number. So I 0.1 would be the second bit within the first byte of the controller. IB1 would be input byte, and the starting address would be 1, so it would be all 8 bits in byte number 1. IW2 would consist of byte number 2 and byte number 3 in the controller. ID4 would be a 32-bit double word. That would consist of byte 4, byte 5, byte 6, and byte 7 in the controller. And the addressing is the same whether it's an input, an output, bit memory. When it comes to data block references, we do use a slightly different syntax, but the concept is the same. If you want to access an individual bit within a data block, first you have to specify the data block number, so in this case db10 dot, and then you use the syntax dbx for data block bit, and then you specify byte.bit. So the .dbx 0.1 would be the second bit within the first byte of the data block. db10.dbb1 would be data block byte number 1. So technically it would be the second byte in the controller. db10.dbw2 would be starting at byte number 2, and it would use bytes 2 and 3 to represent a 16-bit word memory location. .dbd, data block double, and starting byte address 4 would use bytes 4, 5, 6, and 7 to represent a 32-bit word memory location. So here is the actual syntax for absolute addressing of your inputs, outputs, and M memory. So for an individual bit, you would specify the memory area, and that would either be an I, Q, or an M. You specify the starting byte number, dot, and then the bit number 0 through 7 within the byte that you want to reference. So some examples would be I 0.1 or Q 0.1. For a byte address, you specify the memory area, I, Q, or M, and then you use the letter B for a byte reference, and then specify the byte number. So examples would be IB1, QB1. For a word address, you would specify the memory area I, Q, or M, and then you use W to specify a word, and then the starting byte number. So examples would be IW2 or QW2 for input word 2 or output word 2. A double word address would be the memory area, I, Q, or M, and then use a D for a double, and then specify the starting byte number. So examples would be ID4 or QD4. And then the syntax for addressing the data block is listed. So for a bit, you would specify the data block number .dbx, which stands for data block bit, and then specify the byte.bit number in the data block that you want to reference. So an example, db10.dbx 0.1. For a byte address, you specify the data block number .dbb for data block byte, and then specify the starting byte number. For a word address, it would be the data block number .dbw and the starting byte number for your word address. And for a double word, it would be .dbd for data block double and the starting byte number. I will open up my hardware configuration for my project. I will select the local I/O module, which is an 8-channel digital input, 8-channel digital output card, and select Edit Symbols. So on this card, the addresses are I0.0 through I0.7 for the inputs, and Q0.0 through Q0.7 for the outputs. So the starting byte address for the inputs was set to 0. The starting byte address for the outputs on this card was set to 0 as well. So in my program, I could use I0.0 or Q0.0. I will close this out. I will select my remote I/O node, and I will select the 2-channel analog input card and select Edit Symbols. This 2-channel analog input card, the starting byte address was set to 256. So for the first analog input, IW256 would use bytes 256 and 257. The second analog input would use bytes 258 and 259 to represent your analog values. So in your program, you could use IW256 or IW258. And we'll select Close, and I will open up the help and select Contents. And I will expand out the appendix In the appendix, you can find quite a bit of information about the memory areas in the CPU. So you can find a definition of the load and work memory. You can find information about the different areas of the system memory. And then under data types, I can expand out the elementary data types. Select elementary data types, and this would list out all of the elementary data types in the controller. I will scroll down so that you can see the rest of them. There are complex data types. So I'll select the overview for the complex data types. Complex data types are data types that define groups of data that are larger than 32 bits or consisting of multiple data types. So things like strings, arrays, UDTs, etc. would be considered complex data types. In addition to the elementary and complex data types, you can define parameter types for formal parameters that are transferred between blocks in the controller. In this lesson, we covered CPU memory areas and addressing.